All right, our next presenter, Christopher Johnson, is presenting on leveraging custom automation to generate 3D transportation models. Christopher was born in the computer-aided drafting and design through his father, a mechanical engineer, and an early adapter when pencil was placed by the digitizer. After receiving a BS in mechanical engineering himself, Christopher continued a technology-focused career path as a lead technician on the 3 largest transportation projects in Wisconsin. He is now a regional resource for setting drafting and modeling standards, developing automation applications, generating visualizations from three-dimensional models, and integrating CIM practices into large transportation projects. Without further delay, Christopher Johnson.
Thank you so much. I'm really grateful for the fact that we've got this many people. It's the 11th hour, and it's been a long couple days, long session, and I really want to honor your time. I spent a lot of effort of my own to really hone this in and bring as much value as I possibly could in the next 30 minutes. I'm going to do my best to really trim that down and get you guys some content really quickly and really clearly. So I'm comfortable with questions if you want to wait till the end, or if there's something that I'm communicating that doesn't make sense, feel free to stop me. So information plus automation equals value. During this presentation, I'm going to invite you to think about information as energy. Now, how I'm going to communicate this is with this kind of 4-legged roadmap. I'm going to go through the products, the processes, and then have some comments at the end about how this ties into maintaining data asset value through the life cycle of a project. So I'm going to begin at the end and hopefully as painlessly as possible attempt to pull up a video that I may just consider the last one here. So here's the end product, the end goal. And for this particular task, this is the Portsmouth Bypass project, the 16-mile P3. And what you're looking at, the sole purpose initially was intended for a communication tool for the shareholders of the project. And so the model you're looking at is comprised of existing terrain model, an existing vegetation model, proposed roadway. This is an edited 60-second clip, and it's just demonstrating the size, magnitude of the model that was developed for this communication tool. All right, great. So what I'm really doing is I'm exploiting this task, this project of creating a visualization for communication.
I realize that I should give a little maybe disclaimer, warn you perhaps, of 2 faux pas that I've got in my presentation.
I will not say anything more about that. So as I was saying before, I so rudely interrupted myself. The process is providing me with this excuse to show you a little bit more under the hood. How did I deliver this communication tool in approximately a tenth, literally about a tenth of the time that it typically takes to generate that size and magnitude of a 3D model content. And so I'm going to also highlight the asset value of not only the models themselves, but of the tools, the custom tools that were developed to deliver that process and increase efficiency. And when I use that word, for the most part, I'm talking about things like MicroStation VBA, which is a programming language, as well as open source tools that I'll be sharing with you during this presentation how they are available to you. So in order to communicate this equation, so to speak, of information plus automation equals value, I'm going to demonstrate this with a couple examples of the models that I produced. I'm going to use this three-step process, essentially. I'm going to talk about the available data, the accessible tools, and then the output of the data that ended up delivering value and how. So the first of four examples of models that were used, with this kind of heuristic or approach in mind is a 3D roadway model. And so I'm showing here the data that was available. This is data that was delivered to the contractor, the electronic deliverable, after the design was complete. And then on the bottom, I'm showing essentially a process workflow that was used in order to create this model. So I trust this is a pretty familiar picture here. GeoPet cross-sections. These were the design deliverables that was my starting point in order to create the model from. And here's a closer look at one of those source sections. So one of the things that I want to draw your attention to, and I'm going to note several times today in this presentation, is the value of exploiting metadata, otherwise known as attributes. So initially when I had this data, I sat down with a friend and colleague of mine, Joe Everett, a GeoPack expert, and he really helped me understand how to exploit the metadata that was already there. So what I'm showing here is I selected a cell, a GeoPack cell, that's present on each one of these cross-sections, and as you can see, circled in red on the right, it's got a lot of robust data there, more than just pure line work, that's ready to be exploited. Things like the station, the chain name, and the station. And so the first tool that I developed is a VBA tool that I'm referring to here as a trace tool. And what that tool did is essentially trace the top of the finished grade surface in order to produce this visualization model. Because throughout approximately 500 cross-sections, there were, as was mentioned in previous presentations, there's not always consistency between the different legs or different cross-sections that are delivered. So this tool essentially created a visualizable contiguous surface. And in the process, again, what I did is I automated the exploitation of all that metadata that was attached to this, the GeoPack cells themselves. And so I've clicked on the little magenta barrier in the middle of the cross-section. And what you're seeing here is just native MicroStation element information functionality. When you click on it, then what I did is I used an object property handler that I'll share just a briefly general overview of what that is later. But that metadata then that's now associated and attached directly to that element came from and was authored from the design intent that was poured into the previous information state. The next tool is this VBA align. So I'm simply just like using tools and building on the information there to transform it into something that's got more value and carrying that information across with it. So the next tool was a tool that simply took the geometric information that was defined in each one of those cross sections, and it just did the math for me as far as moving it and rotating it three-dimensionally. So this is a screenshot of now the aligned 500 different cross sections. And again, I've selected that same barrier element right in the middle, and I'm just showcasing how, without any more intent, effort, or attention from myself, that metadata was carried along to that element. And so it enabled me then to take this skeleton structure, so to speak, and then create another tool to simply stretch a mesh skin over that framework. And I had everything I needed at this point because with the metadata, it gave me the chain name to use, so I could do this by chain. It gave me the station number, so I could just order them by station in order for this end result. So next I'm going to talk about now the next model, the 3D ground model. And in order to generate this model, the available data is listed here, the accessible tools, which is a combination of some open source tools, as well as some custom VBAs, and then the workflow process in the bottom. And I've listed this URL link on the bottom of the majority of these slides that I'll make a little bigger at the end. And that is a website that I set up that's going to have all the content that I'm sharing with you here, not only in presentation form, but all of these links to the tools, and even the tools that I developed that I'm sharing with you here are accessible through that link. So the first step in this process is to take the data that I acquired from OGRIP. That it's very similar data that can be accessed from USGS, the NED, National Elevation Database. And what you're looking at here is a screen capture of three-dimensional ranges that are colored according to far, mid, and near. Those are boxes that I generated automatically with another tool, simply just exploiting the metadata files that accompanied the OGRIP LiDAR files. So I'm going to zoom into the bluish blob region. And this shows just one of those sections. Again, keep in mind that those red boxes, which were the near, that represents the 16 miles of this P3 project. So this is just a small portion of the data that was accessible to me and that I downloaded. This is one section of that LiDAR, and as you can see, with the labels kind of help me identify and work with this stuff. And again, kind of parking on this metadata facet functionality, the classification is something that's embedded within all of these LiDAR files. They can also be known as point clouds or by their file extension, an LAS or LAZ file. And embedded within each of those files is not only their geospatial coordinates, but other metadata such as classification. So here we're looking at just the vegetation classification. Here in white, the unclassified points, which reflects things like structures, buildings, and bridges, as well as some utilities. And then in red are the existing ground or the bare ground, the bare earth classified points. And so this takes me to showing very simply a couple of command lines that are used for an open source tool that's called LAS tools. And the first line of this code, essentially, as I've listed there, it's filtering out and just going to give me exactly what I need. In this case, it's the ground. The next line reduces those points because it actually has a higher precision than I need for this intent. So the next tool that I developed was one that essentially takes all of those filtered output from the LAS tools, which were in simply just ASCII files, and I automated the batch processing of consuming all of that data using inroads to generate automatically DTM files that therefore could be displayed with 3D graphics. And so that's what, this is a mesh, wire mesh of the triangulation. So next, in order to make this existing ground model look pretty, here's the available data, the tools, and the workflow process for creating imagery material. So again, I exploited the data that's available from the OGRIP site, and I've got to say, from working on a number of projects, and prior to this particular one, I've been using USGS a lot. The OGRIP website is got a great variety of data types and really great accurate data relative to a lot of other states. So it's really something that's valuable and worthwhile to exploit and get familiar with. So again, going off of the near and mid and far approach to applying materials that I use for generating the existing ground, the shapes that are shown here, again, are related to the metadata that's attached to these images. And so I used two open source tools at the beginning to really provide for me the images that I needed in the format that was useful for the microstation materials. The first tool was one that took a Mr. SID file, which I was not familiar with this before I dove into this, but a Mr. SID file is, as you're aware of that have used it, it's very, very large. One of the really neat things about this Mr. SID file that gives it the efficiency in navigating at various scales is the fact that the SID file actually contains in itself multiple scales. You know, just like the Google Earth approach, when you zoom from far out to far near, it's actually costing your computer performance less taxing because it's utilizing the benefit of scale. And so the first command line essentially took this large Mr. SID file and it exported for me very large JPEGs in 3 different scales. The next command line took those various far, near, and mid scaled or resolution images and chopped them up into the right sizes that I need for my materials. So here's a screenshot of what all of the existing ground surfaces look like as they're colorized in their different sections. This is out-of-the-box microstation functionality for creating an elevation drape material, which is essentially, you know, when you've looked at Google Earth, it's taking an orthogonal image and just draping it straight vertically down on the Earth. And so I've highlighted in red just some of the pertinent settings in order to create a material like this. And then once it's applied to the entire surface, this is the result as it's rendered with a smooth rendering in the view. And as you'll note, there's an area in white there, and that's essentially what this surface would look like without this material attached to it. So here's a closer perspective, looking at the existing terrain with the interior boundaries that are not there, and that's just out-of-the-box functionality from the modeling platform. And then the ultimate conditions that are reflected when you just join the existing conditions with a proposed model. So finally, the last example is an example of creating a 3D vegetation model. Now, for those of you who saw the animation that I shared with you, and you thought to yourself, what the heck, Chris, the trees look kind of wonky. I agree. I'd say the same thing, and I get it, because there's a lot of slicker, prettier tools out there, such as RPCs that you could use, which stands for Rich Photorealistic Content. It's essentially just purchasable 3D cells that have got excellent quality photorealistic images of things like trees on them. But the reason that I didn't take that approach with this is that is twofold, and it's exploiting this approach of information plus automation to get value. So the reality with this LiDAR data that's classified is it's actually reflecting survey-accurate geospatial points, data. And I've got a head shake there, and I chose the term survey-accurate, and the head shake is very appropriate because there's different scales of precision. And so the scale of precision here is actually higher than what's needed for visualization purposes. However, because of its precision, it could be exploited to provide value in unexpected ways. So an example of what I mean by how would you get value from using LiDAR for a tree model is once this data gets used to create a model that could be viewed by the contractor, it gives the contractor the opportunity to provide feedback about something like, hey, why is there vegetation in my staging area? That feedback can come to the department and can trigger things that I've got several anecdotes of this really happening with other projects of ancillary value coming from feedback that we get of, hey, why in the heck does it look like this? So the fact that I can exploit these billions of points to create accurate data, I'm not using the word survey, I'll use LiDAR, it gives me the potential for unexpected value. So here again, my first starting point is these classified LiDAR points, and this is the vegetation. So next, I created a mesh tool, very similar to the tool that I used for the 3D existing ground. And I'm going to zoom into the area in that magenta box, otherwise known as color 6. Here is the initial output of those vegetation, that vegetation model. And as you can see, it's just the top of the trees. But in order to actually produce something that's accurate to visually represent what the trees are, then I created a tool which essentially automated the process of taking those mesh elements and draping their boundaries onto the existing ground that was made in previous steps. And that gave me the ability to then produce the finished vegetation model that could be used in the large visualization. So before I go any further, and this is now kind of taking me around the home stretch with this, I want to really leave you with as much value as I possibly can. And one of the things that's been so critical for me and of fundamental importance with being able to capture the value in the information all along is metadata. And so programmatically, this is something that's called an object property handler that was applied to elements. And it's directly connected to these elements. So that means that anytime you move them, whether or not you authored that metadata yourself, it's maintained and it carries across through any time that element is used. So I'll share two anecdotes about examples of how unexpected value came from exploiting this methodology. This is an email that I got from my client, ODOT, and they asked, hey, can we reduce the tree height by 25%? So, sure, this task would only require manipulating about 8 million-ish points across 100,000 different elements. But I could do it. And the reason I could do it is because I utilized existing tools and just refurbished them in order to deliver and address this comment. So what would have otherwise taken me weeks to do manually, I was able to spend 4 to 8 hours on refurbishing a tool and then leave for the day and have it processed for me. Again, another example of just exploiting the value of the tool assets themselves is another comment from that same email about differentiating between the grass for the slopes and the rock cut face to produce this product. And so the tool that was used in order to help automate this process is demonstrated here. And essentially, I'm using tools and applications that I previously wrote and just refurbished and combined them to do this task here. So what I'm demonstrating is I've got these line strings that define the edge of those two faces. I'll select that. I'll select one of those interior shapes, and then the tool essentially just selects that contiguous area up into a range. All right, so this takes me to now just a few comments before my conclusions here that I want to share with you. And this has to do with, again, this concept of capturing the value in your data assets. So here's an illustration that I'll just let speak for itself for a few moments. Now the illustration on the bottom there, that's the typical treatment of data that I'm familiar with, that I use. So this is a slide from a presentation that I gave at 2015 TRB in a workshop for digital data standards for project delivery. And the punchline for this slide here is a punchline that was hammered on by Mark when he first opened up, as far as just evolving standards. You know, for those of you who remember beta, this kind of speaks for itself. And similarly, you know, in your presentation, Mark, if I understood it right, you know, between 2013-ish, when there was pilots and releases of things, until now, there was 3 different versions of a Bentley software. So like there's 2, 3, and 4 in there. So change is inevitable. Another slide from that same presentation is to highlight that there's 5 different platforms that were used in this process of generating a deliverable model, and 7 different file formats that were used within that process. Now, my punchline for this is not that that's a bad thing, and not that that's something that should be done away with. To try to just expound upon that a little bit, it was shared in all 3 presentations that you heard before this. You know, one was, I remember yesterday at the CAD workshop, where Eric Thomas mentioned about the complexity of an inroads template. And you mentioned it as well. And you can get so complex that as a tool is no longer beneficial for anybody but that one person who developed it. And similarly, in, I believe it was Steve's presentation, he showcased, it was the Business Center tool, Heavy Construction Edition. And if you ask the question, why did he use that and not show MicroStation or Civil 3D being used, it's because there's very specific functionality that actually is required to produce a constructible model, using a term that was used earlier, versus a design model. And so there's different tools that are needed for different jobs. And then a point, this is taken from the ODOT CAD manual. And the thing I want to highlight here is that ODOT specifies acceptance of products that were delivered both from Autodesk platforms and a Bentley platform. And this is what I call a project-based specification, or sorry, a performance-based specification. It's something that prioritizes what was delivered above and beyond how it was delivered. And then lastly, this is a admittedly oversimplified caricature of an illustration. But the main point here is just to kind of visually highlight that there are differences in the interoperability that's available to you based upon the platform that you choose. Not all software is created equal. So a couple of the conclusions. One, the only constant is change. Expect the unexpected. Why not posture yourself to expect that there will be a change in formats? Secondly, one size does not fit all. You're going to use the right tool for the right job. So why would you mandate what is the only one tool that could be used to rule them all? And lastly, all software is not created equal. If interoperability is identified as a value to you in order to capture the value of your assets through the life cycle of a project, then it makes sense to plan and expect for that with a very flexible platform. And so here's my last words. Custom automation. Use it to fix your asset pipeline leaks. At worst, it's like duct tape. Quick and easy one-time fixes. But things that actually do help you maintain the value of your data assets. But at best, they can be like gold. Reusable, appreciating assets themselves. Not only able to maintain the value of your data assets, but actually themselves provide you valuable assets that can be built on and leveraged in unexpected ways in the future. So with that, I really appreciate your attention at the end of the day here. Here's that link that I mentioned gives you access to all of the information and content and resources that I shared. And I'd love to get some questions and comments.